So today we discuss a dielectric of an atomic view. Dielectric of an atomic view. So previous class we discussed what when dielectric put on a to equipotential surface, what happened. Okay, what a change value of capacitance of that took place. Okay, here discuss here. Okay, effect of dielectric on capacitance. Now we discuss today is what is dielectric. Okay, the dielectric of an atomic view. So first is a polar dielectric. Polar electric. So what is polar dielectric? So polar molecules like H2O have permanent electric dipole moment. We know that. Okay. So their orientation now look like this. Okay. Their orientation now look like this. Here, suppose there is a random orientation. Okay. There is a random orientation. Suppose that's minus plus plus minus. We choose the random orientation minus plus. So because they have a polar molecule, they have plus minus direction. So they have a dipole moment in that direction P. If dipole moment is present, so obviously electric field plus to minus direction obviously. Okay. So that is the orientation like plus minus plus minus plus plus minus plus minus. We choose that randomly. Okay, that's not any perfect orientation. In polar dielectric, so they have so these are called dielectric material. So they have a permanent dipole moment. Okay, so they have created. Now, if I choose a non-polar dielectric, suppose there's a non-polar dielectric. Okay, so non-polar dielectric material have no permanent dipole moment. Okay, so when non-polar dielectric material atoms are put in an external electric field or placed in an external electric field, so that's the external electric field here. These are the external electric field. When non-polar dielectric materials means they have no permanent dipole moment. When a non-polar material placed in an external electric field, now that non-polar dielectric material gets some dipole moment. Okay, so orientation now look like this. Their orientation like this. So electric field in that direction means that is here plus, that is minus. Here the plus, that is minus, plus 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 minus. Okay. Now that dielectric non-polar have a dipole moment. Okay. So minus to plus direction, that's the dipole moment. But opposite create an external electric field. Okay. So that molecule have if plus and minus, so there is an electric field, but that electric field is opposite of the external electric field. Okay. Now that field is applied and some there is an alignment here. Okay. Before that a polar dielectric material have a random orientation, random alignment here, but here is a perfectly placed alignment here. So this diagram I elaborate more or discuss here. Before that, suppose the non-polar dielectric, that non-polar dielectric before applied an external electric field, non-polar dielectric the neutral. Okay, that okay, part A diagram, there is a neutral, so no external electric field here, and this circle represents the neutral. These atoms are neutral. Now this diagram number B. So we put an external electric field here. How? We put a parallel plate here. Put a parallel plate here. Parallel plate. We put parallel plate here, and there is a positive charge. That is a positive charge here. Means two equipotential circles, obviously. That is a negative charge here, and that is actually a capacitor. Okay, so there is an external electric field in that direction, and that external electric field created by these two equipotential circles. Okay, now these molecule, okay, these neutral molecule or non-polar dielectric molecules have perfectly changed that circular shape to a oval shape. To oval shape. To oval shape. Change their circular to oval shape. Circular shape to oval shape. This dotted line means before we applied external electric field, they look like a circular. After that, when I place an external electric field, their shape change and look like an oval shape. So means that a positive here, negative in that direction. So positive to negative, plus, minus, plus, minus, plus, minus, plus, minus. Now actually, so P in that direction, dipole moment, but this molecule create an electric field, okay, and that electric field in that direction, opposite of that external electric field, and that electric field name that is called E plus. Any name, so choose the E plus, and E plus created by that non-polar dielectric atoms, and they are in opposite of that original electric field or external electric field in that direction. That is the E plus. And now the final electric field E, that is equal to E naught minus E plus, and the final electric field in that direction, obviously, okay, and the final electric field and E naught both have same direction, but final electric field has the less magnitude than original or external electric field E naught, because they are due to that slab, okay. Orientation. Okay, so now that's the change in electric field here. So here change slightly decrease electric field. Okay. Okay. Now write a note. Okay. If you're interested to write a note down, please pause the video and write down that notes here. And otherwise, you can write your own notes. Okay. Okay, in Word, that's very good. Otherwise, you pause the video and write down a notes. Okay. So here the diagram A, this diagram A, first diagram actually here, the initial electric field inside, the initial electric field that is equal to 0. So non-polar dielectric slab is 0. Okay. So after that, applied a external electric field. So after that, applied external electric field. Okay. So atom dipole moment have stretched. So slightly stretched, and this circular shape now change into the oval shape here. Slightly stretched here. Okay. Slight orientation obviously did a change here. So there the circle represent electrically neutral. There is a slab. So these are called a slab. These are called a slab. Before that, this is a circle, and this circle represent neutral, electrically neutral, and electric field is applied via the charge capacitor plate, and that is electric field is applied via charge capacitor plate. These are the charge capacitor plate. Okay, and the field slightly stretch the atom, and the atom is slightly stretched here. Okay, that does not look like a circular. Okay, now stretch, and there is a plus minus charge here. Okay, and the separation produce the charges on slab, and these are called slab actually. These are not a four atoms here. There is a huge number of, suppose there is a billion number of atoms here. So that's called a slab. These are called a slab, dielectric slab. These are called a dielectric slab. Okay. So there is some vector value. So if I vector electric is a vector quantity, if I show that final electric is lesser than the charge capacitor electric field. Okay, previous electric field. Okay, when no dielectric here. Okay, clear. Next we discuss dielectric and Gauss's law. Dielectric and Gauss's law. That's a very important concept. Similar diagram here. Okay, this diagram I put same diagram here. Suppose that is there is a two slab here. Two slab. I think these two slab is a equipotential surface. Obviously, these two are the equipotential surface. Okay, so the plus charge lower part of the upper surface, and that is a minus here. Now we put a dielectric slab here. Now we put a dielectric slab here. This slab here. These are the dielectric slab here. This is non-polar dielectric slab here. Same that diagram obviously. Okay, the same as that diagram. So there, top of that slab, one external electric field. That external electric field in that direction. Okay. There is an external electric field, and here external electric field created by these two parallel plate or charge capacitor. And now the slab has upper part with a negative here, and lower part with a positive here. Okay, you see the diagram before. There is the upper part. See that here. So if plus that equipotential surface, this surface a plus charge here. Now slab has negative charge here, minus, 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 and if minus of charge capacitor surface here, So there is a plus atoms, okay, plus charge of atoms, of slabs atoms. Now if I say that a charge Q here, plus Q, and the slab charge is called minus Q dash, and say that a plus Q dash and minus Q charge here, capacitor, and that is dielectric slab. Dielectric slab. Okay, so that electric refuse that a plus to minus direction electric field here. Okay, and this external now represent that E0 in previous diagram. I represent that E0, and that is a E plus here, and the final electric field is E, that is equal to E0 minus vectorically obviously E plus. Okay, now we apply Gauss's law here. We apply Gauss's law in that surface. Here apply a Gauss's law. When you apply this is called a Gaussian surface. Surface, that is the area A of that surface, obviously lower part of the surface here. This surface with the area A. Okay, that's the Gaussian surface. Now when you apply Gaussian surface here, okay, so that is equal to epsilon naught phi means E dot dA. So a small amount of surface here called dA, and dA direction in same direction obviously, and finally electric field obviously in same direction. That is charge enclosed. That is a basic Gaussian surface here. Okay, and you see that actually this charge enclosed is less, that is a plus charge here, and there is a minus charge here, and that is charge equals the plus charge, that is equal to plus Q. Okay, and if I say that plus Q is called suppose 100 coulomb, and the minus Q is called minus 10 coulomb. So final charge enclosed by the surface, the absolute value is that 100 minus 10, that is 90. So Q minus Q dash, that is charge enclosed. Okay, and that is epsilon naught. E and dA are both in same direction, so cos 0. A dot B means AB cos theta, cos 0 beta 1. So epsilon naught E and integration of dA, that is equal to get A, EA, that is Q plus Q minus Q dash, and these Q dash are the charge of the slab, dielectric slab in the upper part. Okay, that is minus charge. And here we get electric field E, that is equal to Q minus Q dash over epsilon naught times A. So in new page, give that equation number 1. Okay, so here the electric field is taken with weaker, and that final electric field, the final is weaker than before when you put a dielectric slab. Okay, so here that is a electric field, final electric, obviously the final electric weaker than external before that dielectric slab put place here, that is some factor K. Okay, so weaker than some factor by K. So electric field, the final electric field, obviously final electric field is weaker than before. Before means when dielectric slab is not placed here. Okay, and that is the factor by, so the factor by K. Okay, the factor by K, that is E0, that is Q over the charge Q over epsilon naught A times K, that is equation number 2. If I 1 equal to 2, okay, 1 equal to 2. So that is equal to Q over epsilon naught AK, that is equal to Q minus Q dash over epsilon naught AK. Okay. So not K here, obviously, sorry. Cancel epsilon naught. So we get Q by K, that is equal to Q minus Q dash. Okay, so Q minus Q dash. So that's the important factor. When a K puts here, so K, when a K equal to 1, when we put K some factor K that is equal to 1, so that is Q equal to Q minus Q dash, and that's 2 Q are cancelled, so Q dash be the 0. So Q dash be the 0 represent that is no dielectric, means a vacuum. So means a no dielectric, actually no dielectric present, no dielectric present. So Q dash be the 0. So Q dash actually the upper part of the charge, okay, dielectric. Okay. So if a upper part charge be the 0, so means no dielectric slab here. That is mean actually vacuum. Okay. Otherwise, now that modify the Gauss's law, that is epsilon naught, and that some factor K introduce E dot dA, that is equal to charge. Now Gauss's law is modified by here, they are introduced is there some factor K. Okay, now here we see that is the Gauss's law of dielectric, and epsilon naught Ke. Now this change epsilon naught, these are that these three terms epsilon naught K and E. And what is K? K is a factor, and K is another name, is good name, is called dielectric constant. Dielectric constant, the factor dielectric constant, and the electric field E as a vector, we get D. And what is D? And D is called the electric displacement. Electric displacement, and this is a vector quantity. Okay, and now this Gauss's law of dielectric is modified here. So that is epsilon naught Ke replaced by D dot dA, we get Q, and this Q is charge enclosed by the Gaussian surface. Okay, and this charge Q, okay, is enclosed by the Gaussian surface, by enclosed Gaussian surface, means actually Q equal to, before the dielectric place here in dielectric slab here, that is Q minus, say the Q final, say that is a Q dash, and this Q dash are created by the generated by the dielectric slab here. You say that is a Q dash here. Okay, that is a Q dash here. Okay. Now that's the modified Gaussian law of dielectrics. Okay, and that is a, we taken the Gaussian surface, and these Gaussians are not taken as free charge only. Okay, is now taken Gaussian surface is now taken free charge only. Okay, and this induced surface charge is ignored actually, and now the ignore induced surface charge. Okay, and now the dielectric constant K, actually the K dielectric constant, and that is obviously the important factor, that is equal to epsilon by epsilon naught, and we know that, okay, from previous class, and that is a K. Okay, that actually now that is epsilon naught. Now the epsilon naught, that is free space. Okay, permittivity of free space now change. Okay, So now the epsilon equal to k times epsilon naught. So before when k equal to 1, that is epsilon equal to epsilon naught, means no slab here, okay, actually no dielectric put in that capacitor. So that's why k equal to 1. Otherwise there is some factor k, and this k factor came from this dielectric slab, okay, this dielectric slab. Okay, then mainly and k part we put mainly k part in left side. Okay, so that's the clear concept of what is the k and what is dielectric constant and what is the electric displacement, and electric displacement is the vector quantity, and here the k equal to epsilon by epsilon naught, and the k equal to 1 when that is no dielectric slab here, that is the permittivity free space, and that is equal to free space of both are the same, permittivity of the same. So now that factor is k depending on that. Okay. So we complete that chapter 2, and next class we solve some important numericals. Okay. If any doubt in the chapter 2 in any portion, okay, so always welcome in comment section. Okay. So today end the class here. Thank you.